My name is Robert Diesa III. I'm a student of Ty Lidman's at NC State. I'd like to thank the nearly carbon neutral organizers as well as the organizers of the Floer topic group for the invitation and opportunity to speak. We'll be going over Heegaard Floer homology, an extremely useful approach to studying low-dimensional topology problems over the past 20 years, and immersed curves, which is a highly geometric way of encoding Heegaard Floer information for manifolds with boundary. And usually there's hope that you can recover some Heegaard Floer information for a full 3 manifold. All right, so to start, we'll start with a closed orientable 3 manifold Y. Unless stated otherwise, all manifolds will be like this. Ojot and Sabo associate to it a finitely generated vector space over the field with 2 elements, which we'll call HF hat of Y, which decomposes over spin C structures on Y. If you'd like, you can think of these as non-vanishing vector fields modulo some equivalence relation. And we'll denote the spin C summands like this. Just a few properties. It's equipped with a relative Z grading. We'll typically call this the Maslov grading. There's a non-triviality result that the dimension is greater than or equal to 1 if, for each spin C structure, if Y is a rational homology sphere. And when you have equality for each spin C structure, Y is called an L space. And this is generalizing the situation for lens spaces. We also have something called the mapping cone formula, which relates the Heegaard Floer homology for P over Q Dehn surgery along a knot to the full knot Floer complex of that knot. So bridging knot Floer homology and Heegaard Floer homology. This is a reminder, P over Q Dehn surgery, this means is you take a knot complement in the 3 sphere, you glue back in its wake a solid torus, but now you send this meridional curve on the solid torus to some PQ curve in the boundary of the knot exterior. Okay, so maybe we'll take a look at some things that Heegaard Floer homology has been incredibly useful and very helpful to study. A slight note right before that is we'll pretty much only talk about the hat flavor of Heegaard Floer homology. There's also the plus and minus flavors and the infinity flavor as well. Right, so 2 big open problems involving Dehn surgery and for which Heegaard Floer homology has been very helpful for are the cosmetic surgery conjecture and the cabling conjecture. This first is asking when different surgery slopes along the same knot, if it's possible that you could have orientation preserving diffeomorphic results. And towards looking at this has been approached using the topic of this talk, immersed curves, by Jonathan Hanselman. And we'll mention more of this later. The cabling conjecture, which asks when surgery on a knot is reducible or it contains an essential 2 sphere by which you could then split the pieces. The conjecture asserts that this is possible only if K is a cable knot and the single surgery slope is given by a specific integer related to that cable. This has been approached using Floer homology by the mapping cone formula that I mentioned earlier, by Jen Hom, Ty Lidman, and Nick Zufelt. Okay, but generally, things that are very nice maybe tend to be hard to compute, and that has been the case for Heegaard Floer homology. So that introduces the divide and conquer technique, thanks to Lipschitz, Ojot, and Thurston, which they provide through bordered Heegaard Floer homology, a way to compute HF hat of Y. So what you do is you take your three manifold Y and you break it up into two halves, and you relate them by gluing along those boundaries, such as H here from the boundary of M1 to the boundary of M0, that should say. You want it to be orientation reversing homeomorphism. While this isn't a necessary condition to assume, for this talk, we'll have M0 and M1 both having a sharing torus boundary. So what are some of the pieces needed to understand their invariant? We need the torus algebra, which we'll call A, script A, and this is generated over our field with two elements by Rabe chords, row 1, row 2, row 3, and idempotence iota 0 and iota 1. Multiplication here is conveniently described by this quiver on the left, where the filled-in dot represents an iota 0 generator, the open one an iota 1 generator, and then the Rabe chords relating them. We also have trivial relations. Row 3, row 2 is 0, and row 2, row 1 is 0. And then convenient shorthands, where we might write like row 1, row 2, row 3. Shorten that down to row 1, 2, 3. And some modules over this torus algebra. First, we have CFA hat for our first split apart manifold torus boundary. This is considered a type A structure. The alpha 0 and beta 0 in the notation give you a boundary parameterization for its torus boundary. And this is more directly, it's a right A infinity module over the torus algebra. And then analogously, in a dual sense, we have the type D structure, CFD hat, and maybe we won't get too involved with these, but some examples maybe for type D structures. For the solid torus, it has a single iota 1 generator, and then a single Rabe chord describing the map on the type D structure, which is just a row 2, 3. And then on the right here, we have the type D structure for the trefoil exterior with the standard meridian longitude basis for the exterior, and its maps describing the delta multiplication map on the type D structure. Right, so why introduce these structures? This is due to the Lipschitz-Oswald and Thurston pairing theorem, which if we have Y decomposed as the way we had it before, then the Floer homology for Y can be recovered by taking the type A structure for one component, the type D structure for the other half, where here the gluing map sees some play with the boundary parameterization. And you take the box tensor product of this and the homology of that chain complex. That's a mouthful, but it ends up also being quite involved. Thankfully, though, Hanselman, Rasmussen, and Watson associate to a manifold torus boundary and immersed curves invariant. So they take, for the type D structure at hand, they take something algebraic and code a lot of its information very geometrically. The notation for this will also be HF hat of M. This can be possibly confusing, but just know that if the argument on the interior is a closed 3-manifold or a manifold of torus boundary, and that'll let you know which ones we prefer to. So this is a collection of immersed curves in the punctured torus. So the torus boundary torus with a marked point removed. Also, it can possibly be decorated with local systems. This is not something that is encountered often. I won't really mention anything beyond it, but just know that there's possibly a bit more information layered onto this invariant. Right, so some examples of this, we saw the type B structure for the solid torus before, and here's the curve invariant for the solid torus on the left. It's just a homotopic to the homological longitude. And on the right, we have the immersed curves invariant for N. This is the neighborhood of a Klein bottle in a closed orientable three manifold. It also goes by the name of the twisted I bundle over the Klein bottle. The shape of its immersed curve makes this a interesting object to glue with others to see study whether or not you can get L spaces as results or not. Okay, so here were just two examples of immersed curves. There's an algorithm if you start with a valence 2 decorated graph for your type D structure to reconstruct the curve invariant. And a valence 2 decorated graph is exactly what we had up here with the trefoil exterior. So what you do is you take the edges in the directed graph, and depending on the labels, you connect the different iota 0 and iota 1 generators in the torus boundary. So you embed the iota 0 generators along the vertical segments and the iota 1 generators along the horizontal ones, and then fill in the arcs between them depending on the maps in the directed graph. And this is done on the right for the trefoil exterior. And this is pretty dense in the trefoil, or in the torus boundary. So we can lift this to the plane on the left. And if we start at, say, this box square shape, we could follow the curves and recover this lambda periodic immersed curve. And then on the right is shown if you just lift to the infinite cylinder with all of the lifts of the mark point deleted as well. So typically this is the immersed curve to have in mind for the trefoil exterior, is the one on the bottom right. All right. And so we had the pairing theorem for bordered invariants. We hope that we also have it for immersed curves. And this is the result due to Hanselman, Rasmussen, and Watson, that the Floer homology of a three-manifold Y can be recovered by decomposing it like before and taking the intersection Floer homology of the immersed curves of its components. I'll let L sub R be the inclusion of the curve invariant for the solid torus, but it has a slope R due to maybe the gluing that recovers like slope R Dehn surgery. And then LRN will be a lift of that slope R line, but through maybe height N in the plane. So we can come back to what that says about Floer homology, but an example of this is here. So we have 2 surgery on the right-handed trefoil. This is also presentable as filling the trefoil exterior with a solid torus that has slope 2, such as here. And we see the straight line red curve associated to the solid torus filling with slope 2. And then in our notation, this is the L20 cuts through at height 0 here, and then L21 cuts through at height 1 in the plane there. Should note that this is height 0 in the tiled plane where we're lifting our curves. In the puncture torus on the left, maybe this is TM. I can be a bit more specific. It's T of the trefoil exterior. We have 2 intersections. And if we just lifted a single red curve to the tiled plane, we would only ever recover one intersection. So we need two lifts. Coincidentally, this is a slope 2 filling curve. It ends up being the case generally. And something that we end up with is that the Floer homology in what we'll call the 0th spin-C structure is given by the intersection Floer homology for taking the curve invariant for the trefoil exterior and then intersecting it with this line of slope 2 through height 0. Using the immersed curves pairing theorem here to compute that. We end up with rank 1 Floer homology in both spin-C structures, which means that this is an L space. An example where we don't get an L space is, say, the same surgery slope, 2 surgery, but this time on the trefoil exterior. Sorry, not this time on the figure 8 complement. So the figure 8 knot 4-1, its immersed curve is shown on the left. Here we have this T in the complement of 4-1. One thing to notice is, true to its name, it has a figure 8, which is interesting, but also it has this curve, this white arrow there. This is another feature of the immersed curve invariant when it has multiple components. You see one of the components is a figure 8, the other is a horizontal line. This is what we'll refer to as a grading arrow. This will show up more in the second talk, but when you want to recover the Maslov grading in a given spin-C structure, you need to use these grading arrows to do that. Just for speaking about the dimension of Floer homology, the grading arrows don't make a difference. The lift of a curve intersecting the grading arrow doesn't add any intersections for computing Floer homology that way. Okay, and then this is an example where we have rank 3 Floer homology in one spin-C structure versus rank 2 before. So here we had rank 3, and in this one we had rank 1. So, an example of maybe how do you compute the Maslov grading, we can take this figure 8 example. Generally, within a spin-C structure, the Maslov grading difference between two generators is computed using some bygone P. So maybe, for example, you can look at the one below between from Y0 to X0. And the formula involves the winding number of enclosed base points that P covers, where the mark points are counted with winding, the total counterclockwise rotation along the smooth sections of P, and then the weight of P's is some integer that's tied to the grading arrow itself. This is typically recovered using the full knot Floer complex and information from knot Floer homology. This will also show up a bit more in the second talk. But here in this example, we get that a single base point is enclosed with positive winding. There's no grading arrow to cover, so then plus 0, and then we're minus twice the counterclockwise rotation. Well, the counterclockwise rotation of the smooth sections is just pi. So we end up with 2 minus 1. And so the relative grading difference there is just 1. And we can look over here on the right, there's no base point enclosed. There is a grading arrow to traverse. However, this one actually just has weight 0 anyway. And then the contribution from rotation, you will notice here that there is also pi worth of counterclockwise rotation. So here the grading difference that we get is minus 1. All right. So with those examples out of the way, advertise some recent use of immersed curves. Hanselman used this, as I mentioned earlier, in the topic of the cosmetic surgery conjecture, to severely restrict the possible surgery slopes that could even possibly admit a cosmetic surgery. And the strategy which inspires something for the second talk is to just look at multi-sets, take all of the relatively graded generators and compare that multi-set across Vinci structures to ultimately, conclude that you couldn't have diffeomorphic manifolds. Hom, Kong, and Park used immersed curves to study ribbon knots, where they looked at ribbon knots with strong homotopy fusion number 1, but then arbitrary large fusion number. And I think the suspicion there was that maybe these numbers are close to each other or not, but they came up with examples where they're arbitrarily large. And the distance between them is arbitrarily large. Before, I'd shown using immersed curves in the context of Klein bottles, trying to investigate when a surgery would admit a Klein bottle. And in this case, a lot was known about genus 0 and the single genus 0, and then genus 1 knots admitting surgeries containing Klein bottles. For genus 2, an interesting slope that could happen is 8. And in this case, if your 8 surgery shows up as the twisted eye bundle on one end glued to a 3-sphere knot complement, and you also then contained a Klein bottle, it's a bit contrived, but then the result is that you must have been gluing a solid torus on, and in that case the surgery knot has to be T25, and then it's known the specific manifold that is outputted. Something that I want to advertise though is immersed curve techniques have something additional to say about the cabling conjecture, and just something to recall is that a knot is considered Heegaard Floer thin if every generator of knot Floer homology lies in a single delta grading. So this is take its Alexander grading, subtract from that the Maslov grading, and if every generator has a single delta grading, then it's considered thin. And it's known that alternating knots are thin. This is due to Oshvat and Sabo. And I was curious what whether it can be shown by immersed curves whether thin knots adhere to the cabling conjecture. And so far, I only feel confident saying that thin slice knots satisfy the cabling conjecture. One feature of slice knots is that their Oshvat-Sabo concordance invariant tau is 0. And in that case, when you have when tau is 0, then its curve invariant for the knot complement has a very simple component gamma 0 bar. This is just a horizontal line, and this is something that was seen for the figure 8 complement. One of the components is just a horizontal line, and in this case, I show that they do satisfy it. The general case of K thin without this tau equals 0 assumption is in preparation, close to finished. Okay, in part 2, we'll go into talking about this result a little bit and use more immersed curves and more features of them. Thank you for your time.